problem. That's why it took so long, but it is solved, and there's lots of packages. They shove it on their original corpus, which was to answer this question of what are the topics in the journal Science over time, and that's a very interesting thing. So what are the topics that science has been interested in over the years? CTM is better than LDA. In fact, you can use more topics, and it has more. It's better able to predict hello documents. So you should, if you have a application like this, use CTM over LDA. Okay, good.
So what is an application where you wouldn't use CTM?
Well, I think you should always check, right?
What's the advantage of LDA over CTM?
It is not obvious to me. It's a little bit faster, but that shouldn't be a big constraint. So, yeah. Good. And CTM is the basis for the structural topic model we'll talk about later. Another one we can relax is this one about the symmetric Dirichlet allocation. This problem is quite technical. Wallach, Mimno, and McCollum have a paper about it, about why priors matter. And even though they show very conclusively that just going with the simplifying assumption of symmetric priors is bad, very few people actually take their advice because it's very hard. So they find that if you actually relax this assumption, you get better and more stable topics. And so they check what happens if you make both of the different priors asymmetric and optimize both of them. And it actually turns out that only optimizing the alpha parameter has a significant improvement, that optimizing the beta parameter doesn't do much to benefit and is computationally intensive. Also, running the full model with asymmetric priors is very expensive. So if you actually integrate out and find the ideal solution, it's very, very computationally intensive. But merely optimizing the hyperparameters at the beginning has a similar efficiency gain and is not quite so hard. And the main advantage of doing it with LDA, doing LDA with these asymmetric prior on the alpha, is that we find that the topics are more stable. And so the stop words tend to be allocated to a very specific number of topics so that you can just ignore them. And
so you don't even need to remove them?
That's right. They still recommend doing it if you're interested in, but you can be more conservative. And in general, we're not always sure what words are interesting. You know, there are certain contexts in which words that might be stop words might be interesting. I mean, so the classic story about text analysis, so one of the first applications is to determine who wrote the Federalist Papers. This was a sort of a detective story in the 60s. And to do that, they only use stop words. It turns out that when it comes to personal writing styles, the prevalence of words like of and the is very distinctive from person to person. So stop words can be interesting in certain contexts, and so you don't want to just throw them out with the bathwater, as it were, at the beginning. So, and if you actually do optimize here, the addition of more topics is does not have the same destabilizing effect on the topics that already exist as it does if you don't optimize it. And so, especially in this context, more topics is better than too few. The last assumption we can relax is this about exchangeability of words.
So well, is there a package for the previous slide?
No.
Oh, okay, cool.
No, you have to do it
the old-fashioned way.
That's right. That's part of why people don't do it.
Mm-hmm. Dude, make that package, get famous.
Finally, so we actually cannot relax this assumption here, but we can actually take steps to make it less problematic. So this exchangeability thing is hard, and so we were going to use something called lemmatization. Stemming is basically a cruder version of lemmatization. Lemmatization requires some more natural language processing. So what it does is you look at a sentence, you look at the structure of the words in a sentence, and you learn something about what those words mean. So there are certain words that are written the same. They are the same combination of characters, but they mean very different things, and they might be indicative of different topics. And here's the classic example. Time flies like an arrow. Fruit flies like a banana. So the joke is that in the first sentence, flies is a verb, so time flies like an arrow. In the second sentence, this is a noun phrase. Fruit flies are a type of fruit, and so the words. Sorry.
Fruit flies are a type of insect. A banana is a type of fruit.
Ah, very good. Thank you. Excellent point, Jimbo. Thank you. So yes, fruit flies are a type of insect, and only by looking at the words that are in the same sentence as the word flies are we able to determine which word it is. And so with the bag of words assumption, where we're only looking at the words in a document, we're not going to be able to tell the difference between flies the verb and flies the insect. And this is obviously wrong. So we're learning wrong things by not lemmatizing.
Sorry, what is lemmatizing?
Yeah, I should be more specific about this. Lemmatizing is breaking down each token, each actual word into the lemma, which is the underlying part of speech, the specific meaning of the word. So it is, in addition to the actual string of characters, it contains information about tense and part of speech.
So in here it's weird because if you were to tokenize or whatever, like stem flies, it would be fly for both words.
Yes.
So it's still like an ambiguous thing, but there could be words which would even like stem differently, right?
There are words that would stem differently but might be the same lemma. That's right. So if the in English,
It's not like a one-to-one mapping for the stemming.
No.
How do you even decide?
stemming just chops off the. Stemming is very crude. I think that you should be careful about when you use stemming, and I think you should use lemmatizing, but it's sometimes hard. Yeah. So especially if we have ran and run. Stemming is not going to pick up on the fact that they're different words. Lemmatization is going to pick up on the fact that they are the same word, right? Because the way we just change the vowel to change the tense, lemmatization is going to tell us that they are in fact the same word.
But I thought that there are all these like dictionaries that serve as inputs.
Mm-hmm.
But so wouldn't it be super easy to just collect like all verbs in English and their past tenses, and then you could just at least get these ones right?
Well, that is what lemmatization is, exactly.
Okay.
Yeah, I mean that's part of it. That's part of it.
So when you've lemmatized it, then you put it into your document term matrix.
Yes.
And the words are now you'll have flies the verb and flies the noun.
That's right.
And then you'll be able to.
Well, so yeah, yes.
That's way more. So I guess like to see that run and ran is the same word,
Mm-hmm.
you could do it with a dictionary, but to see that like whether flies a verb
Mm-hmm.
or a noun, how can you do it? Like you need some like artificial intelligence for that.
Well, yes. There's a whole field of artificial intelligence called natural language processing, and that is how you do lemmatization. But it's really hard to do. It's difficult to install the software. Yeah, Jim and I had to spend some time on that. That's the only time I've had to actually open up the old straight up Perl scripts in the command prompt. Yeah, I mean, I can't even really talk about it, it's so hard. And it doesn't always work very well without hand processing. So when I ran this lemmatization process on my Spanish Twitter data, over 25% of the tokens came back as unknown. And so because they were using slang, because they were using bad grammar, because of all these problems, the data was basically useless after you lemmatized it. And even if you lemmatize stuff that's a bit more serious writing, so the speech of people in Congress or whatever, they're still not always going to work. And so if you really want it to work well, you have to go through and manually replace the words for which it doesn't work, which is time consuming, but which does lead to a better performing model. But this is why people don't do it.
I mean, listing the quantita that associate these diagrams and diagrams doesn't solve pretty much the problem.
It does not, no. Right, so you can use bigrams and trigrams, that's true. Those are other ways to make tokens. If you just make a token out of the combination of 2 words in a row or 3 words in a row, I think in general, we're not going to see like this phrase repeated too many times in a document, and so we're not going to learn too much about this. So yeah, and there also might be word dependencies in a sentence where there are words that are more than 2 words apart, which tell us something about the words that are going on. That does help, right? You might think biograms, trigrams work. You can use them as inputs into topic models. But it doesn't solve the problem. It helps, but it doesn't solve it. And so finally, let's talk about the structural topic model. I am a big fan of this. It does a lot to make it easy to implement LDA in way, or topic models generally, in ways that we often want to implement them, and it helps solve the problem of multimodality. So when you're actually in the process of assigning or trying to infer these latent values, the distribution of topics over words and words over topics, and words over topics over documents, we can actually model covariates about the documents. Rather than just looking at those documents separately afterwards, we can see how the content of the topic varies according to some covariate. In this case, it can vary with a binary variable right now. So we've defined the topic, and we know that perhaps liberals and conservatives use different words to talk about the same topic. Whereas with LDA, we would only pick up on this by having 2 topics, maybe a liberal guns topic and a conservative guns topic. With STM, we can actually see that this is the same topic, but there are certain words that we might use depending on our ideology.
You said right now only binary. Yes. You can't do continuous yet?
Not for content. For prevalence, so this is the extent to which, this one has to do with the distribution of words over topics. This has to do with the distribution of topics over documents. And this can vary with the categorical and continuous variables. So specifically time, and that's a very common application, is how the topics people talk about change over time. And STM allows you to model that directly.
When you say that it has to be, means that is that computationally not feasible to to vary content by continuously?
The folks, Robert, Stewart, and Tinley just haven't done it yet. I don't think there's anything that would make it impossible. But yeah, no. For now, that's from the R package. Exactly. Yeah. And they've also done a good job of solving this. Well, they haven't solved the problem. I'm very careful about this. But this is an excellent way to deal with the problem and ameliorate its negative effects of multimodality. It's something called spectral initialization, which is a pretty badass name. It uses the spectral theorem, which is I don't want to get too much into it, but the intuition has to do with separability. So if they can find certain anchor words, they have to. You can find an anchor word for each topic and assign that topic to only that one topic, that word to only one topic. You find a word that is definitely indicative of the presence of a topic, and you pin that down. And then we can say that all of the other terms in that beta matrix of words over topics are a combination of these anchor terms. So we use some linear algebra. And in practice, we find that the result is deterministic. So it does not have this problem of only finding the local maximum. So you're going to get the same result using spectral initialization every time, independent of where you start. And that is excellent.